Now we move into tertiary recovery, also called enhanced oil recovery or EOR. At this stage, a large volume of oil still remains in the reservoir after primary and secondary recovery. The remaining oil may be trapped because of capillary forces, poor mobility ratio, high viscosity, or bypassed flow paths. EOR methods are designed to target these more difficult remaining barrels. Tertiary recovery is based on deliberately altering the physical and chemical properties of the rocks and formation fluids to improve oil recovery. This is a very important idea. In primary and secondary recovery, we mainly use or supplement reservoir energy. In tertiary recovery, we go further and intentionally change the flow behavior of the system. These methods can be expensive and technically challenging, but they may unlock a significant amount of remaining oil that would otherwise stay underground. This slide introduces enhanced oil recovery as a family of advanced recovery methods. Broadly, we can divide EOR into thermal methods, chemical methods, and gas-based methods such as CO2 injection. Each method is suitable for certain reservoir types. Heavy oil reservoirs often benefit from thermal methods. Water-flooded reservoirs with poor sweep efficiency may benefit from chemical EOR. Certain light oil reservoirs may respond well to gas injection, especially if miscibility can be achieved. Thermal EOR is particularly important in heavy oil reservoirs because heavy oil is very viscous and does not flow easily at reservoir temperature. By injecting steam, we heat the oil, reduce its viscosity, and improve its mobility. The slide mentions two main steam processes: cyclic steam stimulation and steam flooding. In cyclic steam stimulation, the same well is used for injection and later production. In steam flooding, dedicated injectors and producers are used. The basic principle is simple: heat the oil so it can move more easily. This slide introduces steam-assisted gravity drainage, or SAGD, which is widely used in oil sands and very viscous bitumen reservoirs. The method uses a pair of horizontal wells, with the injector above and the producer below. Steam injected into the upper well heats the bitumen, reducing viscosity. The mobilized bitumen then drains downward by gravity into the lower production well. SAGD is a beautiful example of combining thermal effects with gravity drainage. It is one of the most important thermal recovery technologies for very heavy hydrocarbons. Chemical EOR involves adding chemicals to injected fluids to improve oil recovery. These chemicals may reduce interfacial tension, change wettability, or improve mobility control. Because the interactions among oil, water, rock, and chemicals are very complex, chemical EOR requires careful laboratory testing and field design. The key idea is that chemistry can modify how fluids behave in the pore space. This opens recovery opportunities that are not achievable by simple water injection alone. This slide lists several important chemical EOR methods: surfactant flooding, polymer flooding, alkaline surfactant polymer flooding, and foams. The dishwashing analogy shown here is actually useful. Just as detergent helps remove oil from dishes by changing interfacial behavior, surfactants in a reservoir help mobilize trapped oil. Of course, the subsurface is much more complex than a kitchen sink, but the analogy helps illustrate the basic concept. Surfactant flooding is based on reducing interfacial tension, or IFT, between oil and water. When interfacial tension is high, oil can remain trapped in pore throats by capillary forces. By reducing IFT, surfactants help mobilize the trapped oil. This method is often combined with polymer injection to improve sweep efficiency. Because mobilizing oil is not enough by itself, we also need the displacement process to contact a large portion of the reservoir. This slide likely illustrates how surfactants help EOR. The practical point is that surfactants change the interaction between fluids and the rock surface. They may reduce capillary trapping and, in some systems, alter wettability. This allows more of the residual oil to be mobilized and displaced toward production. Whilst, however, surfactant performance depends strongly on salinity, temperature, rock mineralogy, adsorption, and the composition of the oil and brine. So it is a powerful tool, but not a universal solution. Polymer flooding improves oil recovery mainly by increasing the viscosity of the injected water. When water viscosity increases, water mobility decreases, and the displacement front becomes more stable. This improves aerial and vertical sweep efficiency. In simple words, polymer flooding helps the injected fluid push oil more uniformly instead of fingering through the easiest flow paths. This is especially important in heterogeneous reservoirs where plain water tends to bypass significant volumes of oil. When polymer flooding is being considered, several issues must be evaluated carefully. First is water and polymer compatibility, especially with respect to divalent cations such as calcium and magnesium. Second is thermal and rheological stability. The polymer must remain effective under reservoir temperature and flow conditions. So polymer flooding is not simply about buying a chemical and injecting it. It requires a strong understanding of fluid chemistry, reservoir conditions, and injectivity behavior. This slide shows screening criteria for polymer injection. Screening helps engineers decide whether a reservoir is a good candidate. Typical screening factors include oil viscosity, reservoir temperature, salinity, permeability, and water chemistry. Not every field is suitable for polymer flooding. A good engineer must evaluate the reservoir systematically before recommending the method. ASP stands for alkaline, surfactant, and polymer flooding. This method combines the benefits of each component. Alkaline can react with acidic oil components to generate in situ soaps, surfactant reduces interfacial tension, and polymer improves mobility control and sweep efficiency. The advantage of ASP is synergy. By combining mechanisms, it can achieve higher recovery than using only one component alone. However, the system is also more complex to design and manage. This slide presents screening criteria for ASP injection. As with polymer flooding, careful screening is essential. Factors such as oil composition, reservoir salinity, mineralogy, temperature, and permeability all influence feasibility. ASP can be very effective, but it is also sensitive to chemical loss, adsorption, compatibility, and operational complexity. This slide continues the ASP screening discussion. In practice, engineers need laboratory core flood tests, fluid property measurements, and often simulation studies before field implementation. Because multiple chemical mechanisms interact simultaneously, uncertainty can be significant. This is another reminder that EOR is not only about concept, but about careful technical evaluation. This slide shows the role of field-scale simulation in chemical EOR. Water saturation maps help us see how injected fluids move through the reservoir and how effectively different zones are swept. Simulation is especially valuable in EOR because the physics are complex and field pilots are expensive. By using simulation, we can test alternative designs and better understand how chemical injection may behave before large-scale implementation. This slide highlights interfacial tension reduction at field scale. Lower IFT may improve microscopic displacement efficiency by freeing oil trapped in pore spaces. However, the field scale result depends on whether the chemical front reaches a large enough part of the reservoir. So when interpreting EOR, we must always think at two scales: the pore scale, where trapped oil becomes mobile, and the reservoir scale, where sweep efficiency determines how much of the reservoir is contacted. This slide shows the effect of increasing water viscosity, which is one of the central mechanisms in polymer flooding. When injected water is made more viscous, the mobility ratio improves, and the displacement front becomes more stable. This reduces channeling and fingering. The practical result is better contact between the displacing fluid and the oil-bearing zones. Now we come to a very important modern topic: CO2 EOR. This method injects carbon dioxide into oil reservoirs to enhance oil recovery. But it also has another important dimension: It can contribute to the reduction of CO2 emissions if part of the injected CO2 remains stored underground. So CO2 EOR is interesting because it links conventional petroleum recovery with carbon management and the energy transition. This slide says that CO2 EOR can kill two birds with one stone. That phrase means it can achieve two goals at once: increase crude oil production and help protect the environment by storing CO2 underground. Of course, the full environmental balance depends on project design, monitoring, life cycle emissions, and how much CO2 is permanently retained. But the key idea is that petroleum engineering tools can also support lower carbon strategies. Let us now recap the main ideas from today's lecture. First, oil recovery occurs in stages: primary, secondary, and tertiary recovery. Second, reservoir drive mechanisms are fundamental for understanding primary recovery. Third, we learned about major recovery technologies including water flooding, gas injection, thermal EOR, chemical EOR, and CO2 EOR. Fourth, we saw that advanced methods are needed because large amounts of oil remain underground after primary and secondary recovery. This is the core message of the lecture. Petroleum engineering is not only about finding oil, but about designing better ways to recover it. In the next lecture, we will move to subsurface data analysis. This will be a very useful continuation because every recovery strategy depends on data. To design, monitor, and optimize recovery, we need to analyze reservoir and production data carefully. So please keep today's concepts in mind as a foundation for the next topic. That brings us to the end of today's lecture. Thank you very much for your attention. Recovery methods are one of the most practical and important topics in petroleum engineering because they connect reservoir physics, field operations, economics, and increasingly environmental responsibility. If you have any questions, I would be very happy to discuss them.